the applied perspective. So I joined MLCB, the Machine Learning and Computational Biology Lab, in 2018. And since then, we have tried to push some of the TDA methods more into the machine learning world with some successes, which I'm going to detail to you. And everything happens in the field of graph classification here, so it's much more restricted than what Catherine was talking about, for example. So again, let's talk a little bit about what topology is. So you've seen this, and by now you're already experts on this. But in general, we are interested in studying the abstract shape of objects. And that means with some leeway, with some simplification as to what constitutes shape or not. So for example, this cube here is, for topologists, the same as this sphere, because you can kind of smooth it down. So it's similar to, as a topologist, I would say that my hairstyle is the same as someone who has like a luscious set of hair, because it can be transformed continuously. So, whereas, of course, if we look at this bad boy here, this torus, this donut, this is, of course, to us humans, it's completely different from a sphere. And we try to capture those properties in a meaningful way. So how do we do this? We do it in the simplest way possible. We just count something, because counting is easy, counting is algebra, and we can do algebra. And what do we count? Well, we count d-dimensional wholes. And maybe if you've seen this somewhere before, this is called the Betti number. So the d-dimensional Betti number gives you the number of d-dimensional wholes. And that may sound very abstract, but in lower dimensions at least, you have a very nice intuition behind that. So the 0th dimensional Betti number is your number of connected components. The 1-dimensional Betti number is the number of cycles in your data. And the 2-dimensional Betti number is the number of voids. So if you take this circle here, for example, you have one connected component and one cycle, well, because that's kind of the definition of the whole thing. But if we go a little bit higher and you take the sphere, you don't have a 1-dimensional cycle, but you have a 2-dimensional void inside the sphere. Because for us, spheres are always like hollow. Otherwise, we call them balls. So a ball is something that contains all the points within it, and the sphere is just the surface of that. And if we go even higher, we have this torus here, and for the torus we see some non-trivial cycles happening. So one of the cycles you can already see, that would be this one here. This is one of the cycles. The other one is like kind of goes like this. Anyway, so how could we use this? Well, a simple way to classify objects now would be to just look at their Betti numbers and say, okay, the Betti numbers are different, so the objects must be different, because Betti numbers are invariant with respect to what we call homeomorphisms. And so this works quite well. So we're done, and we can tell a sphere from a torus without doing too many calculations. And this is precisely interesting because we don't need any coordinates for that. So everything happens here without looking at geometry or the actual embedding. We just look at the connectivity. Of course, this has a precise mathematical machinery behind it, which I can't go into the details here, but at least we can sort of approximate everything, what we know about the shape of objects now, in the graph domain. So, given a simple graph like this one here, what could be its shape? Well, in topological terms, we have multiple ways of expressing that shape. So we have the connected components here. So we have all the points that are red and all the points that are blue. So it has two connected components. That works quite well so far. We can go one higher. We can say there are also some cycles. Here are some of them visualized. So a cycle can be anything that starts at one node and ends at the same node without using any edge twice. So there are some cycles. That's also good. That's also a shape feature of a graph. We can go one higher, of course. We can look at cliques. So cliques are fully connected subgraphs of some dimensionality. So this is a 2-clique because it's a subgraph that consists of a k-clique is a graph that consists of k plus 1 nodes. So any triangle is like a 2-clique. These are some of them. These are not all of them. And we can go even higher. We can look at 3-cliques. So if we switch this here out, you can see there are some edges here. So this is a fully connected subgraph, and so it forms a 3-clique as well. So these are our shape features which we will be looking at in a graph. But we already run into some kind of issue. Because what we want to have is, if you come from the rigid mathematical side, you want to classify your graphs up to isomorphism. But isomorphism is a very restrictive setting because you can easily make two graphs non-isomorphic by just changing a single edge. So for example, we look at those two graphs here. So this is the one, this is the other. We would probably say that they are quite similar, except for this one pesky little edge in here. And this destroys the isomorphism for us because we cannot map everything in one graph to the other graph. So if we were to blindly calculate the Betti numbers, the number of cliques, the number of cycles, the number of whatever, we would find that this doesn't work and that the two graphs are different. But we don't want that. We want an invariant, or we want a process that tells us that those graphs are not different, but maybe that they're similar. So we want to quantify this in a continuous manner. And this is where persistent homology comes in. And you've seen this so far with the radii, with the disk of increasing radius, but we can also do this for point sets and for graphs that have weights on them. So again, we start with a simple point set, and are now starting to insert edges one by one, following a weight parameter. And we will see later on how this weight parameter can be calculated, or how we can get weights in different kinds of application scenarios. So we start with nothing being connected. So we have 16 connected components. We start to connect a few nodes. We go down to 11 connected components. We connect some more. Suddenly we only have one connected components, but a few cycles. This should be right, by the way. I counted all of them, but let's see. If you find a mistake, let me know. And then we can go even higher, and we get more cycles and more cycles and more cycles. So this kind of works all out. But what we want to do with this information is we want to put the whole filtration process, so the whole process of growing and inserting edges one by one, we want to put this into a single descriptor. And this is what Catherine, what Fred, what Vitaly referred to as the persistence diagram. The persistence diagram contains all these features on two axes. The first axis gives you the creation threshold of a feature, so at which threshold of the graph filtration process the feature occurred for the first time. And the other axis gives you the destruction threshold, or if you want to be a little bit more dramatic, the life and the death thresholds of topological features. And the nice thing is, at least in the graph domain, if we remain at the graph level and if we restrict ourselves to connected components and cycles, we actually have a very nice one-to-one correspondence between points in the persistence diagram and vertices or edges in the graph. So this is quite nice. This is something that you lose when you go to point clouds, which sometimes can make it a little bit harder to estimate or to trace back your topological features to an actual feature in your data. But in the graph domain, kind of have our work cut out for it, which is nice. So having seen how to get those descriptors, why is it called persistence diagram? Well, it's called persistence diagram because the distance to the diagonal is referred to as the persistence, with the caveat that in the beginning, people said, this persistence means kind of like a noise level or a feature level. So things of high persistence were usually considered to be features in a data set, and things of low persistence, points of low persistence, were considered to be noise. But this is changing, as Fred pointed out. So since the noise is not random here, so of course the intuition is that noise is a small scale phenomenon. So everything that happens around the diagonal is probably noise, but that depends very much on the application domain. So for example, in graph classification, we find that we don't need to do any noise removal from the persistence diagram whatsoever, but rather we need to use everything that we can get. We will see this in a few slides. So already we have one simple recipe for the classification process, namely, if we have a weighted graph and which is unlabeled, so just something where we can do our filtration on, then you now know how to calculate persistence diagrams. And it's possible, you've seen this in the previous talk, that there are distance measures or metrics between persistence diagrams. So you could calculate a kernel based on them or a distance between them. And then you could train a classifier on that kernel matrix, or you could train a classifier based on the distances. And then you would already be able to classify the graphs. So this is kind of nice, but we run into one issue. And that is step number 2 needs to be really, really fast, because calculating this distance in practice can take a long time, because it's an optimal transport-based distance or a Wasserstein-based distance. So this doesn't hold up to some real-world scenarios. And this is where where vectorization or featureization methods come in. And this is what I'm going to talk about in the next slides. So a simple feature vector representation, which we're going to look at now, comes directly from the persistence diagram itself. It's referred to as persistence images, and it's basically a two-dimensional binning of a persistence diagram over a grid. So you get a grid, and then you perform a Gaussian smoothing over all the grid cells. And since you specified the grid dimensions beforehand, you can unroll that grid into a nice feature vector of a fixed size. And in particular, the nice thing is you can increase the resolution as you see fit. We will see this in a second. So how does it work? You take your persistence diagram, you flip it around, so you project that axis to that axis, so that it becomes a diagram in the persistence domain. And then you take the bounding box of your points, and you calculate a matrix. So this matrix looks a little bit, it looks square, even though this is not square, but I did this because it looks nicer if you have square matrices later on. But you can change this, of course. In practice, people use the dimensions of the bounding box of all the persistence diagrams that they have in their training set. And then you just evaluate a Gaussian there. So we can see that there is some density happening at this level, which corresponds to this lump of points, and then there's a little bit more density happening here, but it's of course only 1 point, so we won't see that. So for a single persistence diagram, this looks kind of neat, but it doesn't contain too much information. So the idea is, of course, that you can coarsen that with different resolutions, and you get an increased resolution. You see, okay, now this is really happening, and we have some decrease in density here until we go up in density again. But it really flies when you calculate mean descriptors. So those are now mean persistence images of 3 different classes in a data set. It's a shape data set, if I recall correctly. Don't ask me what they represent, because I have forgotten that, but I could look it up. And you can see that this mean representation is already pretty useful in giving you a way to assess what is going on in your data. And more to the point, this has not been mentioned yet, I think, the space of persistence diagrams is a little bit icky to work with from a mathematical perspective. So it's possible to define means in there, but it's not easy. It involves concepts like a Fréchet mean, and as far as I know, it's not uniquely defined. Whereas if you go into this mean descriptor thing here, just by virtue of featurizing, binning, and gridding everything, you suddenly have a mean representation of one of your classes. And this is, of course, really nice to work with, because you can just unroll that, make it into a long vector, and then you throw it into your SVM or into your neural network or what have you, and suddenly you can do calculations and classifications on topological features. So now how to use this for graph classification. There's actually a super nice paper that came out this year in Europe, which extends this idea, which takes these images here and learns a weight function on the persistence images. So in the original persistence images paper, they just use the matrices that you get, and you unroll everything, and you have your vector, and then you throw it into the classifier, and everything sort of works out. But Zhao and Yusu Wang found out that it actually makes more sense to learn weights on the individual cells of the diagram. And so this is what they did. They created persistence images from a graph filtration. I'm not going to go into the details here, but we'll later see one graph filtration that will always work. And then they learned this weight function on the persistence image by some optimization scheme. And now it's possible to calculate a weighted distance between those images. And this can be used directly as a kernel for an SVM, for a support vector machine. And the funny thing is about this paper, I would definitely recommend reading this. It's not using the labels at all. So it's completely ignoring the label information in the graph. It's just using this filtration and this learned weight function, and yet it outperforms existing methods by far, which is crazy, because usually in graph classification you think that the labels carry some information, but it turns out that if you, at least for the time being, of course, it turns out that if you ignore that information and just learn a good representation of the topology, that this can also be very, very useful. So in the sense, this tells you that the labels are correlated probably with some topological structures in the data set. So I really urge you to read this. It's pretty cool. And the code is open source as far as I know. So now let's move on a little bit. So we've seen how to do this for unlabeled graphs and for weighted graphs. Now let's dive into one of the methods for doing it for labeled graphs, essentially. And this is work that we did last year for ICML, and it involves something that is called the Weisweiler-Lehmann graph counting or graph iteration procedure. And I think everyone here is sort of familiar with it, because who of you has already used a GCN before, a graph convolutional network? Nice. Okay, so this is exactly the procedure underlying the message passing in modern graph neural network architectures. The only difference being that this method, the WL scheme, comes from the 60s, and they didn't have weights back then, and they didn't have neural networks back then. Or well, they kind of did, but no one used them. And so they came from the graph classification domain, we wanted to have an isomorphism test. As it turns out, it's not a real isomorphism test, so you can construct counterexamples, etc., but it's useful to create feature vectors in graphs. And this works in a very simple manner by just looking at neighborhoods. So we take our graphs here, and we look at every node and at its own label, and then we look at the adjacent labels. So we just take a look at the graph structure that we have. We can see that, let's pick one out at random. Let's see, node C, its own label is blue, and it can see blue, 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 and red. So this kind of works, blue, 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 and red. So this works out. We can do this for all the nodes in the graph. And the trick now comes into play. Namely, we hash this label here. So we take those columns together, and we calculate a hash. So we give it a new color. This can use any kind of hashing function. So people have been using a string hashing function, for example. But in any case, we just have to assign a hash that has no collisions, so a perfect hashing scheme. So everything that has a different neighborhood and a unique label should be hashed to a unique hashed label in the end. So for example, you can see that those guys here, A and B, they are completely the same, so they are hashed to the same color, likewise for G. So having done this, we just start counting. So we take those hashed labels that we found in the graph, and we just count how often they occur. So if we go back to the previous table, you should see that it's like 3, 1, 2, 1. And if we have this, we have a way to make our labeled graph into a feature vector. And the feature vector is just determined by the number of labels that we have in the graph in the beginning. And the nice thing is we can iterate this procedure. So we could also make a second step of this iteration. And after assigning these new colors to the graph, we could now repeat the procedure with the new colors and rehash again, rehash again, rehash again, and so on and so forth. And this would make this label vector grow and would give us a more nuanced view into the graph, into higher order neighborhoods in a sense. And the nice thing is this is just an integer vector, so you can plug it into your SVM again, you can evaluate a kernel, you can plug it into a neural network, of course, also, and this gives you a way to classify your graph by featurizing your labels. So this is nice and good, but we can improve it actually, and we can even show some very nice connections here. Namely, if we look at persistent homology, it assesses the relevance of topological features. The WL iteration, the Weisfeller-Lehmann iteration, on the other hand, it vectorizes labels into graphs. So what we can now do is we could combine both of them, and we could get a way to assess, to classify labeled graphs, and learning the relevance of their topological features. And this is what we did last year for an ICML paper. And the only ingredient that we really need for that, everything is already on the table, is we require distance between those multi-sets that we get when we look at the label and at its neighbors. And maybe I'm going to skip over the details, but it's pretty simple actually. It's just you take the labels that you can see, you take their counts, you transform them into another space so that they're just in a count space, and then you can evaluate something like a Minkowski distance or a Euclidean distance. And the important takeaway message is that we now have a metric on the graph defined by the labels. And this is pretty swell. We can do this, it kind of works. So you can calculate the distance between C and E, for example, by looking at their label distribution. So you have 3 blue, 1 red, 2 blue, 1 red, and you get this distance function. We can evaluate this for all the labels. We can get a distance metric on the graph, and we can now filtrate the graph. So this gives us a way to finally assign weights to the graph and calculate persistent homology. And moreover, what we can also do is we can do this for multiple iterations. So this is an adjacency matrix of the graph, and progressively calculating deeper or higher order iterations of this Weisfeller-Lehmann label scheme gives us a better view into how the nodes are related in the graph. So the metric becomes progressively more smooth in the end. And we can now calculate persistence-based feature vectors by basically keeping the whole structure. So recall that in the WL test, you had a feature vector that was indexed by the labels that you get, by the hashed labels. We can do the same thing, and the only thing that we replaced the count function that we had previously here by the persistence function here. So instead of just counting, okay, there are 3 nodes with a blue label or with a greenish label, we just count their persistence. We just sum their persistence with that label. And the same works for cycles, by the way, which the original WL iteration cannot do. So now we have a way to put connected components and cycles into feature vectors for labeled graphs and calculate filtrations from that. And as a bonus, we can also show that the original WL tests, these original features, that they are kind of contained in that framework. So we have subsumed that this original procedure in our topology-based procedure, and it's working rather nicely, I would say. It has favorable performance considering that we can now make use of cycles, and these are just some results on some of the data sets. The code is open source, so you can try it out. It's on GitHub. And finally, we can even, at least in this example, we can even beat some of the methods that are a lot more complicated because they try to use, for example, they try to learn weights on local neighbors, or they try to learn shortest paths with different starting points, things like this. And our method is really simple. It just looks at the topologies, just looks at the metric that we can get, and it still performs quite well. So, having said that, in the last few minutes, I want to briefly cover the new stuff that is going on in the community. So you've already heard about this paper. The new interesting thing would, of course, be to how can you apply neural networks for this classification if you're not restricted to feature vectors. Simple method would be to, again, use persistence diagrams from a graph filtration. And then Hofer et al. Defined a layer to project these persistence diagrams to 1D. They define multiple projections of this, so like 32 or 64, kind of like what you would do in a convolutional neural network. Then you learn those parameters for those projections. You stack the projected diagrams and you use them as features, and you have a way to classify graphs. This was done for unlabeled graphs, though. So they used a graph filtration based on the degree. So it can't use labels yet, but it works quite well for degree-based graphs. It also does something more. So like the graph classification experiment is just one experiment in that paper. One open question, though, that has been sort of dodged for now is how to learn this filtration. So people have been using degree-based filtrations or metric-based filtrations, as I just showed you. But the very interesting thing that is now happening in the community is this so-called graph filtration learning. It's still a preprint by the authors of the previous paper. And the idea here is that you learn an initial node representation on a graph by using, for example, a graph convolutional neural network. Then you calculate the corresponding persistence diagrams, and by applying differentiable coordinate functions of that diagram, so kind of similar to the curves that Fred has shown, for example, you can adjust this learned representation and repeat the process. And by virtue of doing that, in the end, you learn the best representation or the best filtration that you can get to filtrate your graph such that you can express its topology in the most convenient manner. And interestingly, they showed that for some of the datasets that they've been looking at in the previous paper, the degree-based filtration is essentially the optimal one. So kind of their network learned the degree-based filtration in the end, which gives some credence to why people have been using that so far. So that's all I have for you. So let me summarize that. There are 3 ways for TDA-based graph classification right now. So you could either use a filtration plus some feature vectors. You could pump it up a little bit and go to a filtration plus hybrid feature vectors, which is what we did for the WL scheme, where we could use some label information. Or you could go for the filtration plus differentiable feature vectors, which is now ongoing research, I would say. And by that, I'm happy to take any questions now. And I would also like to invite you to join our Slack community, TDA and ML. If you have any questions about TDA, if you want to discuss papers, ideas, and collaborations. So this is just, we kind of kept it open because at every machine learning conference so far, there was quite some interest in TDA, and we had some dinners and talked to people. But now we need a way to maybe connect the community and talk some more and discuss some ideas or applications. So thank you very much for your attention. I'll be happily taking questions now.